Okay, so we're going to talk a little bit about this tray example with the spring. And let's see, let's start by looking at this picture up here. So we've got this tray and we have a spring. The spring is right between like that yellow circle and the green circle. And we want to know how much force do you have to exert where the blue arrow is in order to overcome the force of the spring and lift the tray up. So we've got a little illustration here showing the tray pivot point, the spring anchor point, the spring mounting point, the tray, and the force that's applied to lift the tray. And there's the spring circled. Alright, so we're going to add some arrows here. This is the beginning of our free body diagram. Some arrows that represent the forces that are acting on this tray. So first, starting from the far left, where our yellow dot is, we have two arrows there that are reaction forces. So whatever the tray is mounted to, that object is kind of like pushing back on the tray in X and Y directions. And then we've got the black arrow pointing down into the left from the blue circle. That's the force of the spring pulling down on the tray. We have the force of gravity, the black arrow in the middle pointing down. So the force of gravity is acting on the tray. And then we have the force of the user down at the far right side, the black arrow pushing up on the tray. Now we just put some brackets in here that we're going to use for distances. Before we go any further, Raf, any questions or comments so far?
For the yellow dots, there are two forces, X and Y. Why are they broken out so evenly? Wouldn't it be like a diagonal force going towards the right?
Yeah. So that's a good point. Notice the designations I've used here are PX and RPY.
Oh,
so
breakdown.
Yeah, I've broken out the components of whatever that vector is, that the X on that yellow dot. And the yellow dot, just to remind everyone, that's a pivot axis. So the tray is pivoting on the yellow dot.
So there's going to be a moment coming up soon.
Yep, there are some moments here. Yep. Okay, so let's see. Let's go through these different components here. So we've got RS, which is the force of the spring on the tray.
What is it called, RS?
Reaction force of spring.
Got it.
And then we've got RSX, so that's just the X component of the spring reaction force, and RSY, the Y component. And we've got G, the force due to gravity. We've got FL, which is the lift force over the right side. Our PX, which is the reaction pivot in the X direction.
Reaction pivot.
So it's pivoting on the yellow, right? That's the pivot axis.
So really we're just, it's just a label, pivot, like, okay, pivot at the
It's just a label, yeah. It's arbitrarily labeled by me.
Yeah.
So we've got the X and Y components of that pivot reaction force. And then we've got theta, which is the angle at which the spring is acting on the tray.
What about, can I see the pen, please?
Mm-hmm.
A force from the table going that direction. You have to, for every force, there's an equal opposite force. So the opposite of RPX would be a table exerting the force on that way, right? And we don't put that arrow in, why not?
We don't put that arrow in because we're just looking at the forces that are acting on the tray, not the forces that the tray is producing on something else. That would be a free body diagram for the object to which the tray was mounted to.
So if that's the case, then how come we're putting the force of G here, force of gravity?
Because gravity is acting on the tray. That's a force that's acting on the tray. the free body diagram is all about the forces acting on the object of interest. Does that make sense?
Yeah, this is a new concept. I knew that it was like with the example with the girl on the wall on Cat Academy. Those that have followed for Newton's third law. There's a woman pushing off of a wall when she's swimming, and the force that she exerts on the wall. Okay, so this is the object of interest, and we're only doing the forces that apply to this.
That act on
Thank you.
that body of interest.
Okay, understood.
Yep. Okay. Yeah, it can be confusing to figure out which forces to include in your free body diagram, just like you were saying now. You know, what about the force that the tray is imparting on whatever holds the tray? And always bring yourself back and think about, okay, well, what is the body of interest? In this case, it's the tray. So what are only the forces that are acting on the tray? And that can help clarify it.
Okay.
Okay, so now next step is we're just going to write down all the equations, not necessarily that we need them all, but just so we see all the equations that we could potentially use to solve for FL. Let's see, actually we're solving for RS, aren't we? We're solving for the spring force, I guess. What spring force value RS will allow a user to lift the tray up with a 2-pound force? Okay, so we're saying that FL is given to us, the force, the lift force, that's 2 pounds, and what spring force is required to allow that. So we're writing down all these equations here, and so let's see. Equation number 1, we've got all of the forces acting in the y direction. That's where equation number 1 came from. So looking at this free body diagram, do you see how equation 1 captures all the forces acting in the y direction?
Yes, this is exactly why I didn't understand specifically this, what we're looking at right now, when I was going over the lesson on my own, because I wasn't sure where the equations came from, why each specific force was chosen. But now that you said it's only the forces in the y direction, it makes complete sense.
Okay, cool. And then what about equation number 2? What forces are captured there?
Can we do a white page? Like, I need like something I want to write down.
Sure.
If you could just take a screenshot of this.
Oh, you want a screenshot of this?
And I can just write over it in a different color on top. So the way that I've always done this is the forces in the y direction equals MA. So I'm just gonna write over everything. The mass of what? The table, or the mass of the spring? I'm putting M in there.
Yeah, that's not. I think that's not a super useful equation right here.
What about? We also do this one.
Yeah,
it's the same thing. Just
same thing, right?
We don't use that one.
We're not going to use that one because we're assuming there is no acceleration, and we're just looking at forces, not the force equation, which is mass times acceleration.
What we do here is, though, if there's no acceleration, we turn acceleration into a 0, and then F y divided by m. We multiply by m on both sides, and whatever this m is, it cancels out. So it cancels out here. So really, we end up with. It was F, Y. Okay.
This is really good that you're doing this. If we assume acceleration is 0, which we are assuming, then the sum of the forces equals 0, right? Because mass times 0 acceleration is 0 on the right side of the equation.
So 0 equals the sum of the forces in the y direction.
Yeah. And that's equation number 1, right?
So now, really, I'm just gonna plug in what I see in the y. I see this one, that one, this one, and that one.
Exactly.
And they're all plugged in, and this is gonna be positive, negative, negative, positive, equals 0. So there it is.
That's it. Boom. Yep. So now that we've done some of the forces in the Y.
Done.
Yeah, you can just delete screenshot.
Let's take one more, please.
Okay.
So there can only be, well, actually that's incorrect. I was gonna say there can only be two directions, but you can have more than two directions, right? For f, x, or so I'm thinking if there are only two directions, then why do we have 7 equations?
Well, let's go through these one by one. So we did some of the forces in the Y. Now, what about some of the forces in the X?
I'm thinking why only some?
The summation.
Ah, summation. But why do we have? This is clearly in the X direction.
Mm-hmm.
This is O. No, actually, wait. That's X, Y. Okay.
Just look at the first two equations for now.
Right. So we got this one, and this is going negative. This is going positive. Yeah, I'm just thinking right now, it could be very confusing because if I would have done this on my own, I would have put this right here, that force, and that's a negative force, and I would have used that in my equation, but we don't use it. So a skill is to know which forces to include in your free body diagram. How can one get better at that?
Practice.
Okay.
But
let's keep going.
The arrow that you just drew there, when you set up your free body diagram, you wanna put all the arrows that represent forces acting on the tray. So that red arrow that you just drew there, what force is that? What force would that have been representing?
The tray acting on whatever's holding it. But I'm thinking acting on. Does that mean the force is going into the tray, but not out of the tray? So this one we don't do those. Only the force the arrow is pointing in.
Right. Well, I'm not. That could get confusing. Only the forces. Really, the forces acting on the tray is the right way to say it.
Acting on the tray.
None of the forces of the tray acting on something else.
Well, actually, this FL, the arrow over here, FL, would make me think that this is not a force acting on the arrow, or acting on the tray, because of where this arrow is. It's like it's going to be acting on something here on the air. But really this arrow, if it were here, is the force of the hand acting on the tray. So that's why we included it.
Yeah. Yep.
It's just subtle, very subtle.
Yep. That could be a more clear way of writing that arrow.
Yeah, if I would put it here. Okay, so second equation. Assuming f x equals ma x. Really rearranges to x origin 0, we multiply by m, so it cancels out. So really we just end up with 0 equals fx, and 0 equals, so very important, the minus sign, guys, don't forget that. So minus rsx plus, because it's going to the right, rpx. Is that what we had? Yeah. It's a plus sign over
That's
there.
it. Okay. All right, so there's equation number 2. Now, let's look at equation number 3. Where does that come from?
Screenshot.
This one, I think we can get through this one without a screenshot. Just take a look at that for a few seconds.
RSX squared. So probably trig Rx y a squared plus b squared equals c squared.
That's it.
But that's only when we're trying to find the length of a triangle, but not for the forces.
Well, that's a good point. You can almost think of vectors in free body diagrams, that their lengths representing the forces. So if we draw R sub s and say that's, I don't know, 10 pounds, the component vectors, when we do the trigonometry for them, the units almost don't matter, whether it's pounds or inches or whatever it is. So whether we're solving for a force or a length, it doesn't really matter. Does that make sense?
No, because I was under the impression that we use the a squared plus b squared Pythagorean theorem. Anytime is just to find the length of something, but not the force of a vector.
Yeah, the Pythagorean theorem, it doesn't, it's unit agnostic. The units don't mean anything. They're just numbers. And those numbers could represent a length, or they could represent a force. Heck, they could represent a temperature. The numbers are going to work out the same because the math is the same regardless of the unit.
I'm just googling to use the Pythagorean theorem to find the vector force.
Let's draw something. Oops. Alright, so if we've got, let's say this is our spring force here, this is RS. We've got, break it out into components, RY, or RSX, RSY. If RS equals 10, I can use trig to solve for RS, and we know what theta is. We can use trigonometry to solve for RSX or RSY, right?
No, totally agree. Yeah.
Okay. Now, what if I say this is 10 pounds? Can we still use trig to solve for RSX or RSY?
Yeah, definitely. I understand.
Okay.
I'm just trying to understand why if it's, I mean, the Pythagorean theorem is so much simpler than doing the calculation of sigma f equals ma. The way that I would have done that problem is I would have set up the f equals ma, and I would have used one of the components. So maybe in the y direction, and try to see what else is here.
All we're doing here is writing down all the equations we can think of in case, you know how, like, if you have a certain number of variables, you need a certain number of equations before you can solve for all those variables.
Yeah, so what's the next one? Let's see, number 4. RSX equals RS tangent. If we have the opposite right button. Can you take a screenshot real quick?
Oops.
I'm gonna do this equation here. So I'm gonna do what you try to do. You were trying to find this item here. So you wondered. So And you said I want to find this angle is adjacent. So adjacent. To find the adjacent, I could either have used any of these two, and you decide to use tangent. So tangent of equals opposite over adjacent equals RXY over RSX, then multiply it. Tangent times RSX equals X or Y, hold on, adjacent. What is that? X. Okay. Yeah, just trying to find.
Did it work out?
Yeah, with the X and the Y, I got a little confused there, but it's fine. All right.
Hold on, did I do that wrong? Oh, now I want to look at it. Ah, come on. So let's see, we're doing SOHCAHTOA. So that says tangent theta equals opposite over adjacent. Our opposite is RSY equals RSY. Our adjacent is RSX. SX. So RSX equals RSY over tangent theta. And I have RSY times tangent theta. So it looks like I may have done that one wrong.
Okay. Because it's tangent times RSX equals RSY. And here we have. Can you write the final one, please? How will it come out?
Well, this is it. RSX equals RSY over tangent theta.
So we multiply by 10, multiply by 10. So 10 times RX, right? RSX equals RSY.
Yeah. Yeah, so maybe what I did here is I mixed up my X and my Y. So this should actually be Y, and this should actually be X. Good thing we checked it.
Is that going to affect the calculations later on? Or?
No, because we ended up not using that equation anyway.
Cool.
All right, so equation number 5.
D1 RSY.
So this one might be a little confusing because I don't think we've talked about it a little bit, but maybe not in this context.
This is a moment, obviously, right?
Okay, cool.
So
yeah.
Distance times force equals the moment.
Mm-hmm.
So distance RSY is a force plus 2g. That's another moment minus the third moment. D3 FL equals 0. Okay. Why do they equal 0 if D1 is 1?
So there's a governing equation here. You know how we had sum of the forces equals 0 when there's no acceleration?
You have to set the forces going in one direction equal to the forces going in the other direction.
Mm-hmm. So we said the sum of the forces equals 0, right? For a system in which there's no acceleration.
So I would have done D1 RSY.
What are you trying to solve right now?
I'm trying to set up the initial equation that led you to have this as a final one.
Okay, so you know how we had sum of the forces equals 0? That's how we came up with 1 and 2, equations 1 and 2, right?
Yeah.
There's another one that says sum of the moments also equals 0. for a system in which there's no acceleration.
Is that the very initial equation? Because the very initial equation was this, which ultimately led to 0 equals def. Is this the very first equation, or this is like something derived?
I don't know, but it's where I start when I'm doing moments.
So you said all the moments equal 0.
Some of the moments equal 0 if there's no acceleration in the system. And we are saying there is no acceleration in the system.
This is when the system is at rest.
Correct.
But
Well,
there will be acceleration later when we push on it.
There will, but technically, if all of the moments balance out, if the force required to lift the tray balances out with the spring, then it's like the system is in equilibrium, and just a breath of additional force would then cause the tray to lift up. So really what we're solving for is the state of equilibrium, and we know that if we even add like a fraction of an ounce beyond that, then we'll get motion.
Okay, so this is positive, and this one's negative. RSY. Okay, RSY is going down. G going down. FL going up. So interesting. Usually going down we put negative, and going up we put positive, but we flipped it in this case, right? Is there a reason why?
Yeah. So we're dealing with moments here, not just forces, and so thinking about it in terms of up and down is not the appropriate way to think of a moment, because a moment is rotational, right? Not linear. So for moments, think of it more as like clockwise or counterclockwise, as being your positive or negative.
That's why it's negative. Great, thank you.
Okay.
RSX equals RS cosine. So
yeah, now let's see if I did this trig correct.
So RSX that's gonna be cosine. Let's start from cosine adjacent over hypotenuse, which equals adjacent is RSX over RS. So RS cosine equals RSX. Yeah.
Okay.
And that's the sine is always this side.
Mm-hmm. Yeah.
This is cosine.
Yep. Okay. All right. So these were all the equations that I could come up with for this system here. Not that we need to use all of them.
Let me think about something. When we come up with all the equations, one of them. One of them will be for force in the y, force in the x. This one is the hypotenuse. Then we need to find the sides, and then we do a moments one,
Mm-hmm.
and then also sides. Okay.
Yeah, it's a good checklist. Okay, so let's see. Back to the original question: what vector represents the spring force? What we want to solve? It's RS. This is the value. You gotta get going.
Yeah, that's the way I was supposed to. I'm sorry. Can we leave it off here?
Okay.
Yeah.
If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer or a company interested in training your new engineering hires,
Our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.